In Physics 1402, we're going to be studying something pretty different. This semester emphasizes electricity, magnetism, and electromagnetic waves and light. So everything we learned last semester is going to be important. It's still true. In particular, we need to be able to work with vectors and forces, because electrostatic forces are forces, and they do behave in the same way that mechanical forces or gravitational forces behave. So this first unit, first couple of chapters, is over a field of study called electrostatics. Anytime you hear the word static, think of stationary. Electrostatics is the study of charges that are at rest. Later, we'll study current electricity, which is, of course, electricity that's flowing through conductors. There are some important, just real basic ideas that I feel like you know, but let's go back over them. One is the idea that charge is quantized. When something's quantized, it comes in very definite amounts. In this case, we generally think of all charge being multiples of the elementary charge. And this elementary charge is called E, and it's equal to 1.60 times 10 to the negative 19 coulombs. The coulomb is our SI unit of charge. We have a brand new thing to measure now, and that's charge. For a long time, it was believed, and this is the charge on one electron or one proton, that this was in fact the smallest possible charge. We now know that's not true. We now know that this is actually, there is charge smaller than that of an electron. There's something called a quark. We know that quarks have charges of plus 2/3 E or minus 1/3 E. So we now actually know the smallest charge would be that of 1/3 of the elementary charge. One proton is made up of 2 up quarks and 1 down quark. I know the names are silly, but it actually is made up of a 2/3 E plus another 2/3 E minus a 1/3 E. That's an up quark, and a down quark. So, of course, it has a positive 1 E. One neutron has 1 up quark and 2 down quarks, so it's neutral. We are not going to study these fundamental particles in this course. If you were taking a modern physics course, you might go into great detail. I just want you to know the idea of really what it means to be quantized. You cannot find quarks floating around freely. They've only been observed in laboratory settings. So from a practical standpoint, this elementary charge still holds as the smallest unit of charge found freely, I guess. But we do know that we do have particles smaller than protons and neutrons. We used to think that those were indivisible, but we now know they're actually each made up of 3 quarks. So in the future, it's possible we could find out that quarks are made up of yet some other particle. It still won't change this idea that charge is quantized. You can have 100 electrons worth of charge, but you can't have 100.3. You can't have, it's always got to be an integer multiple of that elementary charge. Another really big idea that's a very fundamental principle is this idea that electric charge is conserved. That means we cannot create electric charge and we cannot destroy electric charge. All we can do is transfer charge from one object to another object, and we can do that fairly easily. Some charges, not all charges. If you have metals that have some loosely held outer electrons, it's fairly easy to transfer a few of those charges. You cannot transfer protons easily because protons are held strongly inside that nucleus by the strong nuclear force. We know that like charges repel and opposite charges attract. Basically, the properties and structure of all matter are due to electrostatics. Why metals are shiny and malleable, why things are brittle. It's electromagnetic charges that hold every molecule in this marker together. It's electromagnetic forces and charge that makes your body function the way it functions. The characteristics and property of all matter comes down to electromagnetic charges. If you observe a force in nature, you're either probably observing a force that is gravitational in origin, that's what happens when you drop something, or you're observing a force that's electromagnetic in origin. Almost all forces that you see are electromagnetic. You just don't think of it that way. We know that ordinary matter is composed of protons, neutrons, and electrons. We know most atoms are neutral. However, if you strip away a few electrons, you can create a positive ion. Or if an atom picks up an extra electron, you can create a negative ion. Most of the time when we talk about the charge of an object, we're really only talking about net charge, excess charge. Again, this marker is made up of billions and billions and billions of protons and neutrons and electrons. It's got lots and lots and lots of charge. However, it's electrically neutral, like most matter. Most matter contains an equal number of protons and electrons, leaving it electrically neutral. When we talk large scale in the universe, like planets and things, gravitational forces are much more significant because every mass in the universe is attracted to every other mass in the universe. However, those large planets, the Earth, Venus, Saturn, the Sun, the Moon, whatever, they tend to be electrically neutral. So even though they're made of lots of charges, electrostatic forces don't impact planetary motion because both objects are neutral. Okay? But when we talk about charged objects, we're talking about net charge. If it's got more protons than electrons, it's going to have a positive net charge. Conversely, if it has more electrons than protons, it's going to have a negative net charge. There are some important numbers you're going to need probably in this chapter. You can look these up easily. I'm not going to write them down. The charge of an electron, or that elementary charge, of course you may want to know, or keep handy. It's 1.6 times 10 to the negative 19. But it's also possible you might need the mass of a proton or a neutron, 1.67 times 10 to the negative 27 kilograms. You might need to know the mass of an electron, which is about 1,800 times smaller. The proton is 1,800 times bigger than the electron. It's 9.11 times 10 to the negative 31 kilograms. But these numbers are in your book. We broadly categorize most materials as either being conductors or insulators. Conductors are typically metals, and they allow electric charges to move freely through them. They get that characteristic because metals have a lot of loosely held outer electrons. If you remember your chemistry, the outer shell of an atom likes to have 8 electrons. Most metals have 1 or 2 in that outer shell. So what they do is they literally give them away. Like a mother that has 12 children and says, I don't need these last couple, somebody take them. So that's what makes them good conductors. By giving away that last 1 or 2 in the outer shell, that next shell down has 8 electrons, and then that metal's perfectly happy. Conductors do not let charge flow. Wood, glass, plastics, rubber, you can think of lots of things. And the reason being is they don't have those loosely held valence electrons. Now, there are a few materials that fall in the middle. Those are called semiconductors. Silicon, graphite. Do you have any others? Those are the 2 I think of. Oh, I didn't even write them down. With a semiconductor, you've all heard about Silicon Valley in California. Silicon is what's been used in lots of diodes and other electronic devices. They act like insulators under certain circumstances, and then they let current flow under others. Because sometimes they won't let current flow and sometimes they will, they actually can behave like switches, on and off switches. Very important in electronics. In addition to what we think of materials that are being as kind of conductors or insulators, we also have ionic solutions. That's generally things like salt water. Water that has ions in it, those charged particles, will behave like a conductor and conduct electricity. Now we talked about the fact that charge is conserved. When we charge something, we don't create electric charge. When you flip a switch, you don't create electric charge. However, we can move charge from one place to another. And we have 2 basic methods. If we want to do it with direct contact, that's charging by conduction. If I have 2 conductors, and the reason I'm picking conductors is because they allow charge to flow easily. If you have 2 insulators and one has a slight charge on it someplace and the other one doesn't, and you bring them in contact, chances are no charge will transfer. Okay. However, it will happen on a metal because we know like charges repel. So if I have 2 metal conductors, this one has a charge of plus Q. This one's completely neutral. We're going to assume they're the same size. I didn't draw them exactly. And I'm going to give them a little wooden handle. Why do I want to give them a little wooden handle? Because I want to have an insulator. So I pick up these, I bring them in contact. Drop my erasers. So I bring them in contact. Now, let's draw this a little differently. Plus Q. One, two, three, 4, 5, 6, 7, 8, 9. What's going to happen when you have a conductor is since the like charges repel, this excess charge is going to spread out evenly over the surface to get as far apart as possible. If I bring something neutral and I bring them into contact, this charge says, oh, hey, wait, I can flow through the conductors. I want to get as far away from possible. And in a minute, you're going to have a situation where the charge has redistributed to get farther apart. If this had a charge of Q to begin with, after we bring them into contact, it now only has Q over 2, and this only has Q over 2. Now, if they're not the exact same surface area, it may not be exactly half. That's why I made them identical. Generally speaking, it's going to be proportional. If this had a surface area of 1 square meter, and this had a surface area of 2 square meters, this one could hold twice as much charge. If that was the case, then the split might look more like this. If this one had twice as much surface area, it would hold twice as much charge. There's nothing fancy or tricky about charging by conduction. It just takes advantage of the fact that like charges, whether those are positive or negative, would like to be as far away from each other as possible, and electrons will flow to make that happen. So in that previous condition, what really happened is the neutral object donated electrons that were attracted over to the positive until both sides were equally charged. The other type of charging is called charging by induction. Now, when we charge by induction, there's actually no direct contact. There's a couple of ways that we could think about this. One is we could just think about, what if I had a piece of metal, well, 2 pieces of metal. It's neutral, but they're in direct contact, so it's almost like I have one long cylinder, except I really know it's 2 pieces. If I bring something over here that's positively charged, well, opposite charges attract. Remember, really only the electrons will move. But what will happen is electrons will travel towards this. So this ends up being negatively charged because those electrons are attracted to this positive. That means this end ends up being positively charged. If we now separate the 2 pieces, and we take away this item, this one will have ended up negatively charged, and this one will have ended up positively charged. We still have conservation of charge, but we used this positively charged object to actually separate charges. Sometimes I call it charge polarization. We get one end to be negative, one end to be positive. Another method that's often used, similar, is we have something neutral. Let's pick one of our metal spheres, and we'll give it a handle again in case I need to hold it. And the charge of the electrons, again, that are free to move, we end up running over here to be close to this. So this side ends up slightly negative, and this side ends up slightly positive. Okay, but it's still neutral. If we take a piece of wire and we connect it to the ground, it can actually be a lot of things, but let's for a moment assume it's actually going to be the Earth. The interesting thing about the Earth is, because of its extreme mass, it contains more positive and negative charges than we can almost imagine. It can gain or lose millions of electrons and still, for practical purposes, be neutral. So what happens if we take a wire and we connect it to the ground? It's called a ground wire. Well, the ground is going to say, oh, look, this is positively charged. And little negative electrons are going to go running up here to try to neutralize it. They're attracted. If we take that ground wire away, we now have, it was neutral, but we've added these electrons. we now have a negatively charged sphere. After we take the ground wire away and we take the positively charged object away. Okay? If we're talking about charging by direct contact, a positive object can give something else a positive charge, or a negative object can give something else a negative charge. But if we're talking about charging by induction, I often call it charging by scaring, because you sometimes feel like you frighten off some of the charge, you scared the positive charges over here. We actually used a positively charged rod to induce a negative charge on that sphere. Okay. Now usually before I reach this point in class, I've already done one of my demonstrations. I'm going to try to do it here. I don't know how well you'll see it in the video, but I'm going to take just 2 ordinary pieces of Scotch tape. Here we go. Scotch brand doesn't have to be Scotch tape. It could be any brand, I'm sure, but it's Scotch tape. Stick it on my table that you can't even see. And stick another piece right on top of it. Now, Scotch tape is not a conductor, but I've got 2 pieces of tape stuck together. And what happens is, if I pull them apart, some of the electrons are actually going to transfer off of this over onto this. That sticky literally pulled some electrons with it. These should be oppositely charged. They are, and you can see that they attract one another. Oh, my black sweater kind of helps. So they attract one another. They want to stick together. Okay, so I have 2 oppositely charged pieces of tape. I'm going to kind of tack them right here and try to save them. I don't want to neutralize them. And I'm going to make 2 more, because if what I've said, those 2 oppositely charged ones attract, I should be able to make 2 like-charged pieces of tape that will repel. So again, I've got 2 pieces. These should also attract. Oh, they do. Okay, so let's see. I've got a lot of tape here. I've got these 2 I know are oppositely charged. Let's see. Do they attract? Oh, look, I think those 2 repel. Now, those 2 really repel. Ooh, maybe these 2 should attract. Those 2 do attract. Kind of tricky, but look, I can't get these 2 to touch each other. They repel. You see them curling away from one another? But these 2 attract. I don't know which one's positive and negative anymore, but I know that these have opposite charges. And yes, these attract, these have opposite charges. And these that repel, these 2 must have like charges. I'm thinking that if I get this other one, it should do just the opposite. These 2 must be like. Let's see. Those look like charges. They're not touching. Oh, those look like opposite. So if you want to have some fun, get yourself some Scotch tape, and you can sure play around with opposite charges attract and like charges repel. Now, one thing that's interesting, I don't know if you've ever noticed this, if you run your comb through your hair or whatever, you can get the comb to be slightly electrically charged. And you can use that comb to then pick up little tiny pieces of paper that are neutral. In fact, I could possibly do it with this tape. And since the tape is sticky, you might just think it was sticking to the tape. Why does sometimes things that are neutral, like little bits of paper, behave electrically? Well, everything's made out of molecules, and most molecules are not symmetric. One side of that molecule may be slightly positive, and another side of that might be slightly negative. If we think about a water molecule, water molecule has one oxygen, that's my oxygen, and then it's got these 2 tiny little hydrogens. The oxygen has, basically they're sharing electrons, but the end result is one side of this molecule is slightly positive and one side of this molecule is slightly negative. We call it a polar molecule. So what happens in a little piece of paper is you get something called charge polarization. If you have a little piece of paper, it's not like a metal. The charges are not free to move around. But if you bring something close to it, say I have a comb here, and after combing my hair, this comb is a little bit positive. What's going to happen is the molecules inside the paper themselves are going to rearrange so that their negative end points towards the comb and the positive end points away. The molecules don't really move, but if all the molecules just kind of reorient themselves, we end up with this side of the paper being slightly negative and this side of the paper being slightly positive, just because of the way the molecules. Well, this slightly negative side then is attractive. Now, charge polarization will never cause repulsion because whatever object you bring near it will attract the molecules. If you bring something positive, it'll attract the negative side of the molecules. If you bring something negative, it will attract the positive side. So it's always attractive. It's never. So you can have a charged object and a neutral object, and they can have an electrostatic attraction. Now, if both objects are charged, it's going to depend on the charges. Like charges, if they are like, they're going to repel. If they're opposite, they're going to attract. But if one is charged and one is neutral, that's always going to be attractive. All right, so we're going to come to the really big formula here. And you should read your text, but I probably just ran through like the first 3 sections of chapter 17. But most of that information, I feel like it's information you learned in a chemistry class or perhaps an easy high school physics class. All right, so this is section 17.4, and it deals with Coulomb's law. It's named after the man who figured it out, Charles Coulomb. He lived from 1736 to 1806. So we're talking 100 years after Isaac Newton. Isaac Newton was born in 1642 and he died in 1727. So Charles Coulomb wasn't even born until after Isaac Newton was dead. So generally our understanding of electricity and magnetism has been behind our understanding of mechanics and motion. He came up with Coulomb's law that said the electrical force is equal to some constant of proportionality we call K times the absolute value of Q1 times Q2 over the distance squared. Now, the absolute values go in there so we don't have to think about whether the charges are positive or negative in order to determine the magnitude of this force. Now, the direction of the force you can't calculate with a formula. We have to actually look at the geometry of the problem. We know it will be along this line between the 2 points. We know if the charges are like charges, they'll be directed away from each other along that line. If they're opposite charges, they'll be attracted to one another along that line. This should look almost familiar. I'm going to put an E here for electrical. It certainly looks a lot like this. It's an inverse square law. If you make the two charged objects twice as far apart, that force falls to 1/4. If you start doubling the magnitude of one charge, you're going to double the force. The only difference is first of all, they have different constants. This is our gravitational constant. K is called Coulomb's constant. And it has a value of 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Notice that's a positive exponent. This really large constant. Electrostatic forces are very strong. I know when we did gravitational forces, I was always emphasizing the fact that they're very weak. So we have a difference that G is a very small number, Coulomb's constant is a very large number. We don't have the absolute values, but it is directly proportional to the size of the masses. Here we're directly proportional to the size of the two charges. But they behave very similarly. We know that Q1 and Q2 are charges, and charge must be measured in terms of coulombs. I know we were just using capital C's last semester, talking about specific heat, calories, and all kinds of things, Celsius temperatures. But when we see just a capital C as a unit, that almost always means coulombs. R, of course, is the distance and has to be in meters. It's a distance between the charges. And K is this Coulomb's constant. K is also expressed a different way. K is equal to 1/4 pi epsilon naught. This is called vacuum permeability. And it equals 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. Now you say, why on earth would I ever want to use this instead of just using this? And the reality is, if we were in a calculus-based course, we would actually find it easier to be using this relationship in Coulomb's law, but we're not. So we'll just use K, which is 8.99 times 10 to the 9th. It's almost 9 times 10 to the 9th. If there's more than one electrical force acting on a charge, then we go back to our mechanics. The net force is the sum of all the forces. It's a vector sum. We really do have to pay very close attention to not only magnitude of these forces, but what is the direction of these forces. Let's do some examples. This is going to be a big formula for you guys, just so you know. That one's going to be important. Our first example says the net charge on a plastic block is -1. So I have a charge, -1.0 microcoulombs. 1 coulomb of charge is huge. The only time we would ever probably talk about that much charge is if we were talking about something like lightning. Now, lightning bolt might have 25 coulombs of charge, but when we're talking about everyday things that we would work with, we're usually going to be looking at microcoulombs or nanocoulombs, maybe millicoulombs, but really small quantities. So if I have a net charge of negative 1.0 microcoulombs, how many more electrons than protons do I have? How many extra or excess electrons is that? It's really easy. We just can almost do it. I have that much charge, micros 10 to the negative 6, and I know that one electron has this much charge, negative 1.60 times 10 to the negative 19 coulombs. If it had a positive charge, we would know that it had excess protons. So I just have to divide, and I see that that comes out to be 6.2 times 10 to the 12 electrons. I just had to divide that charge by the charge on one electron. Another fairly easy example says that they tell us the total charge. They tell us that this object has this many protons, 5.26 times 10 to the 12 protons, and it has 4.82 times 10 to the 12 electrons. And I want to know, what is the net charge? Well, I could calculate the charges on the protons and the charges on the electrons first, but I'd rather just figure out, I have more protons than electrons. Let's just subtract. If I just subtract that, I end up getting 0.44 times 10 to the 12 extra protons. Remember, when something's neutral, we have equal quantities of both, but in this case, we have more protons. I know that if I have that many protons, and I know the charge on one proton is a positive 1.60 times 10 to the negative 19 coulombs, then the net charge works out to be here 7.0 times 10 to the 8 coulombs. Negative 8. Sorry about that. Okay, neither of those used Coulomb's law, but they did help us understand this idea that charge is quantized, and what we're talking about when we talk about net charge. Okay, let's do some Coulomb's law. Let's start with by looking at the electrostatic force within a hydrogen atom. A hydrogen atom which is the world's simplest atom, basically has one proton, and then circling that in the cloud, and we're going to go at the average orbit here, has one electron. They're separated by this radius. Okay? We know that they both have the same charge. Q1 is equal to let's just say, and Q2 equal plus and minus 1.60 times 10 to the negative 19 coulombs. The proton that's in the nucleus has that positive charge, and then the electron that's orbiting has the negative charge. They're separated by what we call in the Bohr model by the radius of 5.29 times 10 to the negative 11 meters. Let's look at two things. Let's look at what the gravitational attraction is between those, and let's look at the electrostatic attraction between them. We'll start with the electrostatic. The electric force is K, which is 8.99 times 10 to the 9th. Q1, 1.60 times 10 to the negative 19. Q2, also 1.60 times 10 to the negative 19. Actually, one of them is negative, but if you'll remember, our formula has these absolute values. So I can just leave that negative off if I want. The distance has to be squared. Let's do a rough order of magnitude. That's 10 to the 9th. That's 10 to the negative 19. So we're at 10 to the negative 10. That's 10 to the negative 29. And this is negative 22. Negative 22, negative 29 on top, negative 22 on the bottom. I'm going to end up with like something maybe on the order of negative 7. Maybe negative 8, because really if we were to round that 8, that's probably more like 10. I think in the order of 10 to the negative 8 or so. We'll see. If I put that in my calculator and punch it all up, it comes out 8.22 times 10 to the negative 8 coulombs. Newton times not coulombs, newtons. It's a force. It's measured in newtons. If I do that same thing, only instead of using the charge on the proton and the electron, I use the masses. I put in capital G. When I do the gravitational force, G is at 6.67 times 10 to the negative 11. We've got the mass of the proton. We've got the mass of the electron. And we've got the distance between them. Notice how small these numbers are going to be. Negative 11, that's going to, with negative 27, that's negative 38. Negative 49, minus 22, like negative 37, something like that. It's going to be way small. I think I did a math there. 38, a mental math there. Oh, that's because this is 31 and I wrote 11. No wonder. Now let's look at that. 11, 38, 69. 69 minus 22 is like 47. It's going to be on the order of negative 47, give or take. Well, sure enough, when we put this in, that force comes out to be 3.63 times 10 to the negative 47 newtons. When I say that electrostatic forces are much stronger than gravitational forces, there's a pretty good explanation right there. Another one is really simple. You can't see it, but right here's a table. Here's a marker. If I drop the marker, it's going to fall towards the earth because of gravity. But it can't get past that table. What's holding the table together? Electrostatic forces. The electrostatic forces that hold the molecules of this table together, that's what provides the normal force, or that support force. That's a much stronger force than the gravitational force when I drop my marker. Okay, carry on. Let's do one more that's going to take us back to, oh, that's right, I have to know how to add vectors. This problem, we have three equal charges. I'm going to draw them in pink. I've got charge A, charge B, charge C. And they're really objects. There's three small charged objects. They are all sitting at the corner of a square. The square is 82 centimeters on each side. And the charge on A, B, and C is all equal. They're all 8.0 times 10 to the negative 15 coulombs. So I have three small positive charges sitting on the corner of the square. We want to calculate three things. We want to calculate one. Let's calculate the force that A exerts on B. Secondly, let's calculate the force that C exerts on B. And finally, let's find the total force on B. All right, let's look at our picture and let's talk about direction because it helps to think before we even start plugging in numbers. A and B have the same charge. They're going to be repelled. So you can see that the force that A exerts on B is going to be this direction. It will be repelled from A. You can also look at the picture that's drawn on this diagonal, and you can see that C will exert a force in that direction. We can stop and think which one will be stronger. Well, all the charges are equal, so since A is closer to B, A will actually exert a larger force than C will, because we know that force decreases as you get farther apart. Okay. And we can even look at it in common sense, our directions. The direction of the force exerted by A will be at 0 degrees, directly to the right. And the force exerted by C will be at 45 degrees. All right, let's see if we can do some calculating. I kind of want to move my picture down low just so we can draw better arrows. So here's A, here's B, here's C, here's our square, 82 centimeters on each side. All I need is a little geometry. I can use the Pythagorean theorem and I can quickly figure out exactly how long this diagonal is. Or I can even use the fact that it's a 45, 45, 90. It's going to be 82 root 2. Now, I'm not really allowed to have final answers with root 2, but for terms of geometry, I can be exact. I'm also going to have to change these from centimeters to meters, but that'll be easy to do. So let's calculate. Let's think about this. We know, we'll call this the force of A on B. And we have a slightly smaller force called C on B. Let's calculate the force of A on B first. That force is equal to K. I'm just going to write K. When I put it in my calculator, I'll have to type in 8.99 times 10 to the 9th. But I know that number, and I might even save it in my calculator. The two charges are 8.0 times 10 to the negative 15. I can square that. 8.0 times equals, so I can over distance squared, 0.82 meters squared. So I very carefully put in the value for K, type everything in nice and neat, and I get that this is equal to 8.57 times 10 to the negative 19 newtons at an angle of 0 degrees. Now, for purposes of answering the question, I should write my answer as 8.6 because I only have two significant digits in the charge, but I'm going to need that third one when I try to add them together. I don't want to round too much. So A on B. If I want to calculate C on B, it looks a lot the same, but the distance is different. It's K, 8.0 times 10 to the negative 15 squared. The distance is 0.82 meters times root 2, all squared. So I'm going to get a smaller force this time. Comes out to be 4.28 times 10 to the negative 19 newtons. And this time I know it's at an angle of 45 degrees. When I get my sig figs right, it looks like this. So there's the answer to A, there's the answer to B. The answer to C is simply the vector sum of this and this. Let's do the vector sum of those two quantities. I'm going to erase my picture so I have some work on that. All right. When I add vectors, and they're not perpendicular to each other, they're not parallel, I have to think of x and y components. How much force is acting in the x direction? Well, all of this plus the x component of this force that's at 45 degrees. So plus 4.28 times 10 to the negative 19 newtons cosine 45 degrees. I could have put cosine 0 degrees next up, and cosine 0 is just 1, so it doesn't do anything. So my x component comes out to be 1.16 times 10 to the negative 18 newtons. The y component is simply 4.28 times 10 to the negative 19 sine 45 degrees. I just had to take the one that was at 45 degrees, get its horizontal component by using cosine 45, get the vertical component by doing sine of 45, and that y component is 3.03 times 10 to the negative 19 newtons. I just have two forces. It's got this much in the x direction, this much in the y direction. To get the magnitude of that total, I do the Pythagorean theorem. So I have to square 1.16 plus 3.03 the magnitude of the force is 1.2 times 10 to the negative 18 newtons. So a little bigger than just which we would expect. The angle, this is going to be a first quadrant angle because the y component and the x component, they're both positive. So I would say theta is the tangent inverse of the y over the x. And that comes out to be exactly 15 degrees. That makes sense. I knew it would be between 0 and 45, but I felt like it should be closer to 0 degrees than 45 degrees because the x component was definitely larger than the y component. All right, so I'm going to stop here. There's a lot to think about, and I'll pick up in the next video. We'll start talking about not just electric forces and Coulomb's law, but the idea of an electric field.